Okay, hi everyone. Thank you for coming. Today we're happy to have with us Jiahe Shen, from a PhD student from Colombia. Now, usually he doesn't work on geometric stuff, not part of our community, but we just saw one of his results on arXiv. We said, wow, this looks really interesting. So we wanted to hear about it and invited him. Thank you for coming to talk to us about it.
Okay, so thanks for invitation and hi everyone, thanks for coming. So today I'm going to talk about the Szemerédi-Trotter theorem over arbitrary field of characteristic zero. So I'm Jiahe and I'm from Columbia University. So this talk is based on my paper, you see, which is available on arXiv. Okay, so as the start, I will introduce the basic object we study. So points and incidences. So suppose we take P, which is a finite set of points, and L, which is a finite set of lines in a plane. So we define the incidence I of P and L to be the number of pairs, small p, small l in P times L, where P lies in L. Okay, so the incidence. So the whole problem is given the sizes of P and L. So we ask how large can this incidence number be? So the Szemerédi-Trotter theorem, classical Szemerédi-Trotter theorem, answers this by giving a sharp upper bound. So as you see, it contains three terms. So there's a main term consisting of this P to the 2/3, L to the 2/3, plus linear terms, P and L. Okay, so this slide shows sharp constructions in three different regimes, and each one comes from a simple best possible strategy. So the first case is that when the point dominates. Okay, so in this case, the best strategy is to put all the points on a line. Here we use a line to pass all those points. Okay, and in this case, it is clear that the number of incidences is roughly the same as the number of points. Okay, so as the dual version, so when the number of lines dominate. Okay, so our best strategy is to make all the lines pass through a single line. And then we put this line in a set of points. So so similarly, you can see that in this case, the number of incidences is roughly the same as the number of lines. Okay. So the most difficult case is a case where P and L are roughly the same size. So in this case, the best strategy is to consider this grid structure. So do you guys know the explicit expression? Do I need to write on the blackboard or? Oh, okay. So you guys are familiar with this. Okay, so then okay. You want me to introduce it? Okay. So
there's plenty of chalk. Good.
Yeah. Okay. So you could consider a countings. Okay. So it goes I J. So and so I reduce over 1 R and A reduce over RX. Okay, so and you take the set of lines to be lines of the form y equals ax plus b. Here, so A is between between 1x and b. Is between 1 and 2 Rx. Okay, so in this case, we have, for example, the size of P is equal to R square x, right? And the size of L is equal to 2R s squared. Okay, and then the number of incidences is I think it's roughly like this. Okay. So and in this case, you can see that it indeed gives a construction that the two-third like the two-third. Okay. So this is the sharp construction, and is it clear to you, or do you want more explanation? Clear? Okay.
I always find it very strange that it just points and lines, and the right answer is two-thirds in the exponent.
Yeah, I mean, this is something very like amazing. Like, I mean, Terry Tao, he has a blog explaining those the proofs and like heuristics about why does this this two-third show up. Yeah, he has like a blog, Szemerédi-Trotter Theorem.
Okay, thank you. I would like to read it.
Yeah. He introduced many ways to prove this. Yeah, there are more than one proof. Yeah. Okay. So, okay, now I place our problem in a context by recalling what is already known in a few other settings. So first is that over the complex case, so like so the sharp bound is the same, like this two-third stuff and two linear terms, and which the result is proved by Tao. And then over finite fields, I mean, there are various Szemerédi-Trotter type bounds. So including, so first the joint work of Bergen, Case, and Tao, which they obtain some non-trivial like improvement. And there's also the proof of the result from Beck, which use some graph theory and etc. And over general fields, so there are improved bounds under additional hypotheses. For example, the joint work of Stevens and D0. So now, so the question highlighted at the top is beyond those special settings or actual assumptions, which is that what can be said over arbitrary fields, like in particular for fields that has characteristic 0. So our main theorem answers this question from the previous slide. So it says that over any field of characteristic 0, so this incidence number satisfies the same sharp bound as the classical Szemerédi-Trotter setting. So you see there's a n to the two-third, n to the two-third shows up, and there's n and n. Okay. So and first of all, and also like this bound is sharp and cannot be improved up to an absolute constant. Okay, so you may wonder how we prove this. So let me explain this to you. So now I introduce the key tool, which I'm calling the Baby Lefschetz principle. So it says the following. So suppose you have an F, which is a field of characteristic 0, and which is also finitely generated over the rational numbers. Okay, so then there exists a field isomorphism. So from F to its image. So the image is a subfield of the complex numbers. Okay, so the takeaway is that we can embed any finite configuration in K. And the K is the field we consider into the complex numbers while preserving all incidence relations. So this slide contains the precise reductions that we need. So the proposition goes like this. So suppose we have, suppose we have a set of points in this K square thing, and suppose we have n lines in K square. So then there exists injective maps. So this is like by P sending P to the complex plane, and this by L sending L to the set of lines in this complex plane, such that it preserves the incidences, which is to say that for all small p in P and small l in L, like P lies in L, and only if and only if the image satisfy the same say with like this P in the complex plane lies in this L in the complex lines. Okay, so it is worth mentioning that we do not embed the whole K square into C square. So, like, I mean, in fact, this can be impossible if K is a very huge field. So, like, but because we only need to embed the finitely many coordinates and coefficients appearing in the configuration. So, you see that, like, to identify a point, you have two coordinates, and like the similar statements holds for the last. Okay. So, based on our preparations, the proof becomes very immediate. So from the previous slide, so we have a way to map off our finite set of points into the complex plane and map our finite set of lines to actual complex lines. So in such a way that the incidences are preserved exactly in this, exactly. So in particular, the number of incidences, okay, does not change. Because we don't create or destroy any incidences throughout this map. And then, so now we are so we have now transferred our problem into the complex setting. So we can directly apply the known Szemerédi-Trotter theorem over the complex numbers. So that gives the upper bound shown on the slide for the incidence number of the embedded configuration. So finally, since the incidence count is identical in the original configuration and in the embedded one, the same bound immediately holds back over our original field. So the Hill argument is that is to preserve incidences, apply an incidence bound, and then transfer the conclusion back, and that completes our proof. Okay, so on the other hand, to give a sharp construction, so let us again recall the real case. So you can also see what's on the blackboard. So in those examples, all the coordinates of the points and all the coefficients. So you have coordinates of the points and coefficients of the line. So they are all rational numbers. So like we can actually regard them as elements in the field K, because the field K has characteristic 0, so it contains the field of rational numbers. Okay, so and this immediately gives the corresponding sharp constructions over K squared. So it shows our bound is sharp in exactly the same sense. And so does anyone have questions? No? Okay. So let's move on. So the classical Szemerédi-Trotter theorem sits right at the interface of discrete geometry and additive combinatorics, and it has many well-known consequences and connections across these areas. So in the same spirit, so in our setting, so once we know that the Szemerédi-Trotter bound holds, we can also recover a family of standard incidence consequences. So one example is this Beck's theorem. So it is like you take a finite set P in this K square, and you let this L of P be the set of lines containing at least 2 points of P. So the Beck's theorem tells you that at least one of the following assumption holds. So either some line contains roughly like a large proportion of the points of P, or I mean this set L of P is like roughly the same size as P squared. Okay, so the proof is again. So if you remember, there's a proposition that we saying that we can transfer like all the points into the complex plane, like without broken, without like destroying or creating new incidences. And in this way, like we can after when we move it to a complex setting, we can and then like since the same result holds for the complex setting, like we can just transfer it back. And so the theorem also holds for arbitrary field for this K, for this field K. Okay. So now let me mention another standard consequences on the additive combinatoric side, which is the Erdős-Szemerédi sum product theorem. Okay, so the story goes like you start with a finite set, subset A of K, and this gives you two sets. So first is the sum set, which consists of elements A plus B with A and B and A, and the other is this product set, which consisting of elements A, B with A times B, with A and B in A. So roughly speaking, this sum product lower bounds is telling you that so it is impossible to let this product and sum set be both very small. Okay, so explicitly like our theorem goes like for a finite set A of K, so the maximum of the sum set and the product set like is like roughly larger or equal to this A to the 4/3 over this log A or 1/3. So up to constants. So okay, so the idea is the same. Like that suppose you have a subset A of K, and you can and you consider the field generated by those elements in A. So this is, and then you can apply the Baby Lefschetz principle. So then you can just bring everything into the complex setting. So in the complex setting, we know that this is this is something we already know, and since this bound holds for the complex case, it also holds for this arbitrary case. So like it is clear that moreover, so if in the future, like the record of this complex case is improved, then like our theorem here can be directly improved following the same way. Okay.
So for example, just as an example, it applies to lots of function fields, for example.
For function field, that's a good question. So for function field, we have characteristic P. So this makes the problem become more difficult because we cannot.
No, but for function fields of characteristic 0 it applies to.
You mean C of something like C of T, right?
Yeah.
For C of T, that's true. This is like for C of T, you get exactly the same bound as C. Yeah, this is quite amazing. Yeah. Does this answer your question?
There's a minor comment. Actually, the best bound is 4/3 plus something like 1/400.
Oh, really?
Yeah.
It is improved?
And so this 4/3 for the reals, at least, is from 2009, 17 years ago. There have been maybe 10 improvements by now, a lot of improvements.
Yeah,
but they always improve by a tiny, tiny bit. And at the moment, it's 1/400 and something.
You mean for the complex setting?
Oh, it's usually easy to, no, that's for the reals, but it's usually easy to adapt these things.
Yeah, but I'm asking for the complex setting.
Right.
So this is the record for the complex setting.
Well, I don't know. Sorry, I'm not. I was talking.
Yeah.
Right.
Yeah, I was also told by like some expert, like there are many people like improving this bound, like many papers. Yeah, but this is the bound like I discovered. Hopefully like it is the correct record, but maybe like someone has already improved this.
No, sorry, I was talking about the reals. You are right.
Yeah, this is the complex, the record for the complex. Okay. So, as a summary, so let me briefly explain the reason why the Baby Lefschetz principle approach works. So the guiding philosophy is the Lefschetz principle. So the Lefschetz principle says that first order sentences have the same true value in all algebraically closed field of characteristic zero. So like this first order sentence is something related to mathematical logic. So you don't need to know the details, but roughly speaking, it is like you say a sentence of finite length, and you only talk about algebra. You don't talk about analysis. It's purely algebra. Okay, so and then the Lefschetz principle is telling you like it doesn't matter which characteristic zero field you choose. And like in particular, the Baby Lefschetz principle is an instantiation of this fact. So and all statements in the above can be phrased as first order statements. So like statements in the above means like Szemerédi-Trotter theorem, Erdős-Szemerédi's sum product, etc. Blah blah blah, and hence it suffices to prove them in the context view C, where we have like an analysis tool to handle for the context setting. So I think it is also reasonable to believe that that our observation can be applied in other instance problems, for example, point curve incidences over characteristic zero fields. Okay. So now let me switch gears and tell a short side story about the original motivation. So I first started thinking about this project when.
Do you want to tell us a little bit? The last time you said other incidence problems like point curve incidences.
Mm-hmm.
So could we be a little more concrete about what you're looking at curves of higher, not just the lines, but curves of higher degree? Or
Yeah. Indeed, yeah.
And then you're asking, so, and then how much of this applies to that situation? So if I look at curves of arbitrary degree or what?
Like the general principle is that if we have a theorem over the complex setting, which is a first order statement, then we can just like then we immediately know that it also holds for arbitrary field of curve.
Yeah, well, I'm not sure what that means. I mean, first order statement. So does that apply to if I write down curves, algebraic curves over a higher degree?
Yeah. I think in general, like if you only talk about algebraic closed things, these are still first order statements. Like
I see.
Yeah.
If it's not a good time for questions, I can ask later. But it gave me a question. Do you happen to know the distinct distances problem? Do you know what that is?
Yeah, I think I've heard of them. Yeah.
Okay.
Yeah, but like
distances, because that doesn't.
Yeah, distances are not first order statements because
I see.
Yeah, like for example, if you consider this is what will be shown up. Like if you consider the p-adic setting, like the distances are like quite different. Like,
but it
like
depends
you're talking about metric on a real setting, so we went that's not the first order statement anymore.
But okay, but let's talk about the complex plane. We can consider the set of all points at some given distance from a given point. It's kind of like a variety around it, kind of like almost a sphere around it, if you understand what I mean. It's you can state it kind of as, okay, maybe we should talk about it later and rather than now. I'm curious to see if it means something about that.
Okay.
Because it's a big problem, and if it goes for arbitrary fields, that would be interesting. Okay, later.
Okay. Let's talk about it. Let's talk about it after our talk.
Yeah.
Okay. So now let me switch gears and tell a short story about the original motivation. So I first started looking at about this project because I wanted to understand a p-adic analog of the Furstenberg set conjecture. So the Furstenberg set conjecture can be regarded as a continuous analog of the Szemerédi-Trotter theorem. So like instead of studying a point line incidences, so like the Furstenberg set conjecture studies incidences between cube and cube. So let me state the definition and the conjecture. So first, the definition of a S-T Furstenberg set is that, so you pick two constants. So S is lies between 0 and 1, and T lies between 0 and 2. So a set E, a subset E of a Euclidean plane is an S-T Furstenberg set if there exists a family of affine lines L such that okay, so the set has dimension, the set of lines has dimension greater or equal to T, and like for each of those lines in L, like its intersection with E has dimension greater or equal to S. Okay, so then the Furstenberg set conjecture.
Sorry, what is H here?
It's the Hausdorff dimension.
It's what?
The Hausdorff dimension.
That's it.
Hausdorff dimension. Oh, yeah, I should have to explain this. Okay, so
Okay.
yeah, so like, and the Furstenberg set conjecture states that the S-T Furstenberg set E satisfies this lower bound. Okay, so what does it mean? So it has three terms, right? So this like brings us into three regimes. Okay, so first we consider the regime, this regime. Okay, so the best strategy is the product of a Cantor set with dimension S and and another Cantor set of dimension T. Okay, so this gives you the dimensions S plus T. Okay. So if so this is the case when R sorry this T. Okay, so and for the case that T is very big, okay, so like T. Okay, so the best strategy is the product of a Cantor set of dimensions and another okay, so and a lot. Okay, so in this case, this construction gives you the force of dimension as possible. Okay, so the most difficult case is that when T lies between these two. Okay, so in this case, the best strategy is a grid construction. So grid, this guy is a grid. So, but I mean, it is like an analog of a grid structure, a fractal grid construction. So in this case, we have force or so I mean, this case turns out to be the most difficult to prove. Okay. So okay, so now let me briefly mention some recent progress on the Furstenberg set conjecture. So one major milestone is a result of opponents working from 2013. So they proved the conjecture in the AD regular case. So very roughly, so AD regular, so it is a quantitative uniformly assumption on a set, saying that the set behaves like an S-dimensional object at all locations and scales. So very roughly, okay. And under that hypothesis, so the conjecture lower bound on a dimension is indeed true. So their approach draws heavily on ideas from projection theory, and it also intersects with some product type input, including what people sometimes call an ABC type, some product theorem. So more recently, so this Ren and Wang, so they proved the full Furstenberg set conjecture. So the broad strategy is multi-scale induction. So they reduce the problem into two model cases, which is the AD regular case already solved by opponent merging. And the other is the semi-well space case. So roughly speaking, so this semi-well space is the case that the tubes are not very concentrated in a few. They are not concentrated in a few clusters. So for that semi-well space case, the coronial ingredient is a high-low method based on harmonic analysis. So before our discussion of the P-adic Furstenberg set conjecture, let me quickly recall the definition of P-adic numbers. So first we have to start with P-adic valuation. So consequently, for a zero rational like x, a non-zero rational, you can always write it as some x equals p to the k a over b, where a, b are integers and not divisible by p. So in this case, like we define we define the valuation to be k of x to be k, and like we also furthermore define the valuation of 0 to be infinity. So the field Q P is the computation of Q with respect to this P-adic absolute value given by this thing. So it is like P to the minus VP of X. So roughly speaking, so the more P that the number X contains, it goes smaller. So okay, so for example, if you take P equals 5, then 125 is a very small number, and conversely, and 1 over 125 is a very big number. Okay, so
you should think of it as like trying to recreate the integers mod p in a field of characteristic 0. So you can't make p actually equal to 0, so you make it very small.
Yes. But QP is still a characteristic 0 field. Yeah. Yes. So then the field of p-adic numbers Q sub p is defined as the computation of the rationals with respect to this absolute value. So it plays the same role as the reals. So so in this case, every non-zero x in QP can be written uniquely as this infinite sum. So this sum converges. So based on our definition, this is a convergence series with k is an integer, and all those ai be in 0, 1, p minus 1. Okay. So since we have defined the p-adic numbers, we now state the p-adic Furstenberg set conjecture. So it has exactly the same three-term shape as in the real Furstenberg conjecture, just transplanted into the p-adic setting. Okay, so you see. Okay, so the Hausdorff dimension also has this exactly the same lower bound as the real setting. So our heuristic is that the recent developed methods for Takeda-type problems, including multi-scale induction, additive combinatorics, high-low method, blah blah blah, can be directly translated in the p-adic setting. So recently, I have been started by looking for people around me to work on this p-adic project. So together with Kevin Ren, so we proved that the p-adic Furstenberg conjecture holds for the semi-well case space case. So and moreover, so together with Yuhan Chu, so we are working on in preparation project that claims that the p-adic Furstenberg sector holds in full generality. Okay. So any questions?